right, so today we're going to talk about molecular geometry. So what does that lead you to believe we're going to be talking about?
Shapes.
The shapes of molecules. Very good. Okay, so molecular geometry is the three-dimensional arrangement of a molecule's atoms within space. So we're going to look at the three-dimensional shape of these molecules. Right? We've looked at the two-dimensional shape in what kind of form, right? What do we call that when we look at the two-dimensional shape? When we draw it? Lewis structures, thank you. Okay. I didn't think it would take quite that long. Okay, the Lewis structures is a two-dimensional representation, right? It's just on paper, it's lines and dots. The molecular geometry is going to allow us to look at the three-dimensional structure, and we're going to use an app on our Chromebook to really let us turn the molecules, rotate them so we can see them in 3D. Okay? When we're talking about the three-dimensional shape, we're going to have to look at electron domains, something called electron domain. Okay, so we look at the number and the type of electron domains to determine its molecular geometry. Okay, and electron domain, the definition is there in parentheses. So how many things are bonded to the central atom, or how many things surround the central atom? That might be an even better definition. Okay, so I'm going to actually make that little edit here. How many things surround the central atom? Okay, because electron domains can contain a bond and they can contain a lone pair. Okay, so when we're talking about molecular geometry, when we just look at the chemical formula of a compound, it's difficult to tell its three-dimensional shape, right? There's no way for us to look at a molecule and automatically know it's trigonoplanar or tetrahedral or whatever, blah, 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 all these different shapes, okay? When we talk about molecular geometry, it's not just like square-shaped or triangle-shaped. Okay, that's not how it goes. There's shape names. But it's difficult to determine that just from the chemical formula. So we have a couple ways and some more rules to determine the molecular geometry of these molecules. Okay, the three-dimensional shape. So to determine an object's or a molecule's three-dimensional shape, we follow what I will call VSEPR theory. Okay, I know that's not exactly how it's spelled, but it's called VSEPR theory. Okay, and this acronym does have a definition with it that you will need to be familiar with. Okay, so VSEPR theory stands for Valence-Shell, Electron-pair, Repulsion theory. Valence-Shell, Electron-pair, Repulsion theory. I would probably tuck that away in your little memory, okay, for what that acronym stands for. Valence-Shell, Electron-pair, Repulsion theory. And this definition will make more sense once we start looking at the rules, so hopefully that will help your memory a little bit with that. But if you think about what it means, right, what does valence-shell mean? The outer, right? What's electron-pair mean? Yeah, a pair of electrons, either a lone pair or in a bond. And what does repulsion mean? They want to go away. Okay, so what this means is that in the outer shell, when we bond electrons, we want them to be as spaced far apart as we can, right? So we want them to orient themselves as far away from each other as they possibly can, okay? That's what that in very general terms means, okay? You can abbreviate this down, okay? But what this means is that the repulsion between sets of valence electrons want to be oriented as far apart as possible. Okay, and that's kind of what we just talked about. Right? If two things repel each other, they want to be as far apart as they possibly can be. So you can just write that little snippet there at the bottom if you want. You can include the whole thing. That's totally up to you. But that's what this means, right? If we've got two pairs of electrons, they don't want to sit right next to each other. They repel, so they want to be as far apart as they possibly can. So we talked about looking at electron domains. Here's the definition for an electron domain, right? Listen. Electron domains are things that surround the central atom. So an electron domain can be a bonding domain or a non-bonding domain. Okay, so electron domains are anything that surrounds the central atom, any little pocket of electrons that surrounds the central atom, A bonding domain means it contains at least one bond. It could contain a double bond or a triple bond. That would still be one domain. Or it could be a non-bonding domain, which contains a lone pair. Okay? Would a non-bonding domain ever contain one single electron? Do we ever let single electrons hang out by themselves? No. So a non-bonding domain always has to contain a pair, right? A lone pair of electrons. A bonding domain, however, can contain a single bond or a double bond or a triple bond that still maintains one domain. Okay, so we're going to count those domains, and it's going to help us determine the shape of our molecule. So when we draw our Lewis structure, we have to be able to determine, do we have a bonding domain or a non-bonding domain? Okay, so we're going to look at total domains, and then we'll look at bonding and non-bonding. So you have to be able to tell the difference between those two. Luckily, they are pretty simple to tell the difference. So for a water molecule, how many total domains do we have? 4 total domains. 1, 2, 3, 4. So 4 total domains. So let's take a look on our molecular geometry sheet. How many different shape possibilities can we have if our central atom has 4 domains?
3.
2.
We have 3 total possibility shapes, right? If we have 4 total domains, go down to 4. Look over. There's 3 possible choices. What are those possible choices? Tetrahedral.
Trigonal pyramid.
Yep. Trigonal, pyramid, and bent. Okay? So, we have 4 total domains. How many are bonding and how many are non-bonding? Okay, so how many bonding? 2. And how many non-bonding? 2. Okay, so we look at our total number of domains on that sheet, right? There's 4. And then we look over to see how many lone pairs do we have in this molecule. How many lone pairs? 2 sets of lone pairs, right? We don't have 4 lone pairs because we have 4 electrons. We have 2 sets of lone pairs. So what would the shape of our molecule be? Bent. Okay, and look at how this is drawn. Bent. Right? Our hydrogens aren't sticking out here. The reason that these are bent is because these electrons, these in the bond and these in the bond, they want to orient themselves as far away as they possibly can. Okay, they don't want to be next to each other, they want to repel each other. So they found an orientation that happens to be 109.5 degrees apart that give them the best possible spacing. Okay? So if you don't have the bond angles written on here, which I don't believe that you do. Oh, are the bond angles written on there? Yeah. Okay, perfect. You'll have to be a little bit familiar with those. Okay, so you need to understand the bond angles, especially for tetrahedral and trigonal planar and things like that.
What are the dotted lines?
Can anyone name this molecule here first? Perfect. Boron trichloride. Very nice. Boron has 3. Chlorine has 7 times 3, which is 21, so 24 total electrons. Which should be our central atom here? No. Boron. The central atom? Farthest away from fluorine? And if there's only one of them, that's typically going to be our central atom. All right, so we've used 6, which leaves us with 18 electrons left. So we want to fill the outer shells of our outer atoms first. And that used all 18 for us, which leaves us with 0. Okay, so are the chlorine octets fulfilled? Yes. Is boron's octet fulfilled? No, but are we okay with that? Yeah, boron is an exception, right? It offers 3 valence electrons, so it's okay if it only has 3 bonds to go with it. Okay? So now let's look at the molecular geometry of boron trichloride. Okay? How many total domains do we have? 3, right? 1, 2, 3. Okay? And how many of those are lone pairs? None, right? No lone pairs surrounding boron itself. So that means no lone pairs. It's not how many lone pairs are in the total molecule. It's how many are around the central atom. So we've got 3 domains, no lone pairs, which gives us what type of shape? Yep, trigonal planar. Trigonal planar. What's it mean to have a plane? Is flat, right? So a trigonal planar means it's just a little triangle, right, kind of shape that's laying flat. One's not sticking out, one's not sticking up. It's just a flat plane, right? So it'll rotate, whatever, but it's laying flat. Okay? And what is the bond angle for this one? 120 degrees. If you are not quite sure yet, I'll just do it up on the board. Okay, we should have used how many electrons here? 32. Good, that's what I had. All right, bromine's in group 7. Carbon has to be our central atom. Are all of our octets here fulfilled? Yes, they look as though they are. So we look at carbon specifically. Carbon has how many total domains surrounding it? 4, good. And how many lone pairs? None. So what would the geometry of this be? Tetrahedral. Okay, so if I was going to draw this 3-dimensionally, it would look something like this. Bromine. Bromine. This guy would be coming out at us here. Bromine. And then there'd be one going back. Bromine. Something like that. Okay, it makes kind of a little triangle base, and then it's got one up at the top. Okay, and I didn't draw that exactly how it should be. The dotted lines usually mean there's one going backward. The wedge shape means there's one coming forward at you. Okay, so what happens here is it forms a little triangle base with those 3 bromines on the bottom, carbons in the middle, and then there's one bromine up at the top. Okay, does that kind of make sense? Again, we're going to look at them 3-dimensionally, I think, next class. But that's essentially what it would look like. Okay? Yeah, you're right. The class after that. Okay, next one, sophomore retreat. So.
Do we get class or
CH2Cl2. Try this one on your own. Both of those hydrogen and both of those chlorines are bonded to carbon. All 4 of those things are bonded to carbon. All right. You'll see anything that has 4 bonds and no lone pairs is tetrahedral. Tetrahedral is extremely common molecular geometry. Okay, so for things that have 4 bonds, no lone pairs, we have a tetrahedral geometry. In this molecule, it didn't matter to us whether we drew the hydrogens opposite of each other or right next to each other or whatever. That really doesn't make a difference. We're not going to get into the technical parts of that right yet. Okay? All right. We already dealt a little bit with lone pairs on the central atom, but we need to understand that these are called non-bonding domains. Okay? On your molecular geometry sheet, it just asks you for lone pairs, which simplifies it a little bit, but we have to understand that that is considered a non-bonding domain because it contains no bonds. Okay? We're not looking at the lone pairs on outer atoms. We're looking at the central atom specifically. All right. Okay, so let's try NH3 here. So the Lewis structure for NH3, do we all agree with this? Okay, how many total domains? 4. 1, 2, 3, 4 on the central atom. How many lone pairs? 1. So we say 4 total domains, 1 lone pair, which means it would be trigonal pyramidal. Okay, and your sheet might just say trigonal pyramid. That's fine. Trigonal pyramidal is usually what I'll say because that's how I learned it. But what's happening here is if we draw this three-dimensionally, it's going to look something like this. Nitrogen in the middle, there's a hydrogen here, a hydrogen coming out at us, a hydrogen in the back, and then these lone pairs kind of pull that whole thing up. So we've got a triangle base, and then that lone pair pulls everything into kind of a pyramid shape, right? Triangle base, one on top. We see kind of a pyramid type shape that goes with that. So that lone pair kind of throws things into a little bit of a tension, right? Because we've got 3 things that are perfectly spaced, and then the lone pair kind of throws everything out of whack. So it kind of pulls that up so we can space them evenly so they can orient themselves as far away as possible. Okay, so it kind of looks like a little pyramid, which is why we get that pyramidal name. Okay, sorry, that's what we just talked about. Lone pair around nitrogen atom occupies space just like the bonds do. The pair wants to be spaced out from the bonds as much as possible. Okay? When we talk about this electron-pair repulsion theory, it's important that we realize the electrons within a lone pair are not going to repel each other, right? One has a positive spin, one has a negative spin, right? We talked about that, so they're going to be okay being next to each other, but the pairs themselves repel other pairs. Okay, so electrons within that lone pair don't repel each other. They don't have to be spaced out, but the pair itself will repel another pair, and it will repel a bond. Okay, does that make sense? So don't start spacing out single electrons. No good. Okay, what about double bonds? How many domains do they account for? 1, right? So any bonding domain could contain 1 bond, or 2 bonds, or 3 bonds, whatever it is. Okay? Multiple bonds leading from one atom to another only count as 1 bonding domain. That might be a good thing for you to have down in your notes, okay? For you to commit to memory. Multiple bonds leading from one atom to another only count as 1 domain. Okay, so let's try a molecule of carbon dioxide. Carbon dioxide, what's the molecule, what's the formula for that? CO2, good. And our central atom here should be carbon. Is this going to work for carbon dioxide? No. Right? This isn't going to work. So what would be our fix here?
Double bond.
Double bond on what side? On both, right? We move this pair of electrons into that double bond. Okay, so now our octets are fulfilled on all 3 of our atoms. We count our total electrons. We have 2, 4, 6, 8. Sorry. 2, 4, 6, 8, 10, 12, 14, 16, which is what we were supposed to have. How many total domains do we have? 2, right? Because each of these are counted as 1 domain. Do we have any lone pairs on our central atom? No, which means what shape are we? Linear. Okay, and that makes sense, right? Nowhere else for these things to go. They're spaced out as far as they possibly can be, which is 180 degrees. They just form a straight line. And there's no reason, they can't possibly be spread any further than 180 degrees. Okay. Feeling okay? All right, let's try the next one on your own. Phosphorus trichloride. Looks like this, okay? And that's what we call trigonal pyramidal. Okay? Very good. All right, last two. I want you to do these on your own. Good. This is arsenic pentafluoride. Our Lewis structure looks good. Our shape was trigonal bipyramidal. Second one was simple, right? Carbon tetrafluoride, which had a molecular